For all of human history, distance was our greatest enemy. Oceans separated civilizations, mountains divided nations. But eventually, we built ships, we built tunnels, we built aircraft. Every time humanity faced a barrier, we created technology that turned impossible distances into ordinary journeys. But space is different. Space is not just another ocean, it is a cosmic abyss. The distance between Earth and Mars can be hundreds of millions of kilometers. The distance between stars is measured not in kilometers, but in light years. Our current spacecraft are powerful, but compared to the scale of the universe, they are barely crawling. The fastest human-made object, the Parker Solar Probe, travels at over 600,000 kilometers per hour. That sounds unbelievable until you realize at that speed, reaching another star would still take thousands of years. The universe is not asking, can we build a faster rocket? It is asking, can we invent an entirely new way to move? Welcome to the Mind Forge. Before discussing futuristic engines, we need to understand the enemy, the rocket equation, created by Russian scientist Konstantin Tsiolkovsky. It describes one brutal reality. A rocket needs fuel to carry fuel that carries fuel. The more fuel you add, the heavier the spacecraft becomes. The heavier the spacecraft becomes, the more fuel you need. It is a vicious cycle. Chemical rockets overcome gravity beautifully, but once you're in space, their greatest strength becomes their weakness. They deliver enormous thrust, but they consume enormous amounts of propellant. The future of space travel requires engines that prioritize efficiency over explosive power. Ion engines take a completely different approach. Instead of creating a powerful explosion, they create a continuous whisper. A gas such as xenon is ionized, meaning electrons are removed, creating charged particles. Electric fields accelerate these ions to extremely high velocities. The result? Very little thrust, but incredible efficiency. A chemical rocket might burn for minutes. An ion engine can operate for years. This creates an interesting trade-off. So let's say a chemical rocket is a sprinter. In that comparison, an ion engine is a marathon runner. The problem? Humans are impatient. A spacecraft with ion propulsion might be perfect for moving cargo around the solar system, but sending astronauts to Mars requires reducing travel time, which leads us to something much, much more powerful. The VASIMR engine attempts to bridge the gap between chemical rockets and ion engines. The name sounds complicated. Variable specific impulse magnetoplasma rocket. But the idea is elegant. Create plasma, heat it, control it with magnetic fields, accelerate it out the back. The engine does not use physical walls to contain the plasma because temperatures are extreme. Instead, magnetic fields act like invisible containers. This is similar to how scientists attempt to control fusion reactions. The exciting part of VASIMR is flexibility. The spacecraft traveling to Mars has two competing goals. One, arrive quickly, and two, use fuel efficiently. These two goals fight one another. High thrust means faster travel time, but more fuel. High efficiency means less fuel, but longer travel time. But VASIMR can adjust between these two modes. It is not a magic engine, will not launch astronauts from Earth's surface. It probably needs a power source in orbit, and producing enough electricity remains a huge challenge. But once assembled in space, it could become a powerful transportation system between planets. Imagine Instead of every spacecraft being a one time expedition, we create space highways. Sometimes the simplest solutions are the most powerful. A nuclear thermal rocket does not create electricity, it directly uses nuclear heat. A reactor heats hydrogen to extremely high temperatures. The hydrogen expands and exits through a nozzle. The physics is the same as a chemical rocket, but the energy source is far more powerful. The advantages are higher efficiency than chemical rockets, faster missions, and less time exposed to radiation during Mars travel. But nuclear rockets have challenges. Launching nuclear material from Earth requires extreme safety measures. The reactor must survive intense conditions. Public acceptance matters. Engineering is not only about what is physically possible, it is what is society willing to build. Imagine a train. A locomotive provides energy. The cars carry cargo. Nuclear electric propulsion works similarly. A nuclear reactor provides continuous electrical power. That electricity runs advanced engines, ion engines, Hall effect thrusters, plasma engines. The spacecraft may accelerate slowly, but it never stops pushing. In deep space, where there is almost no friction, acceleration becomes the key. A spacecraft accelerating at a tiny rate for months can eventually reach incredible speeds. This could transform the solar system from a collection of distant worlds into a connected network. Fusion is the dream. It powers stars. It releases enormous amounts of energy by combining light atomic nuclei. Fusion rocket would essentially carry a controlled star inside a spacecraft. The possibilities are extraordinary. Faster Mars missions, trips to the outer or solar system, potential interstellar missions. But fusion is one of the hardest engineering challenges humanity has ever attempted. The same reaction that powers stars is difficult to maintain on Earth. The temperatures involved are extreme. The materials required are extraordinary. Fusion propulsion is not around the corner, but if achieved, it could mark the moment humanity stops being limited to its planetary neighborhood. Not every spacecraft needs to carry fuel. Solar sails use photons. Light particles have momentum. Normally, this effect is tiny, but with a massive, extremely thin reflective sail, those tiny pushes add up. The advantage, fuel becomes unnecessary. The disadvantage, acceleration is extremely slow. A solar sail is not a rocket, it is a ship that lets physics provide itself the wind. Antimatter represents the extreme limit. When matter and antimatter meet, their mass converts into energy almost completely. Compared with chemical fuel, the energy density is unimaginable. But antimatter has enormous problems. It is difficult to produce. It is extremely difficult to store. Quantities needed for propulsion are far beyond today's technology. Antimatter is not an engineering problem yet. It is a reminder of how much more physics has to offer. The future will probably not belong to one engine. Just like airplanes use different aircraft for different missions, space travel will probably use different propulsion systems. Chemical rockets for leaving planets, ion and VASIMR for moving cargo across the solar system, nuclear propulsion for fast human missions, nuclear fusion for interstellar exploration. The civilization that explores space will not be powered by one invention. It will be powered by an entire ecosystem of technologies. The first humans looked at the stars and saw gods. The next generation looked at them and saw destinations. And the generation after that may look at them and see homes. The engines we build will determine whether humanity remains a single planet species or becomes something far greater. Because the greatest machine humanity will ever build is not a rocket, it is the bridge between worlds. Welcome to the Mind Forge. Keep thinking, keep building, and keep forging the future. Thank you.